Hello, everyone. My name is Kubayama from the West Japan Data Center Division. In this session, I'd like to broaden our perspective slightly from the previous themes of software and AI. I will be discussing the facilities that physically and fundamentally support these services that we are working on every day. This is an unremitting effort to reduce air conditioning power consumption at the Chikugo City Data Center. I will discuss our continuous efforts and their current status. This is today's agenda. In the first half, our role as facility engineers in data centers and as a facility engineer, I will discuss the history of our efforts to reduce air conditioning power consumption from the 2000s to the present day. In the latter half, focusing on the latest approach of AI-driven automatic air conditioning control, its mechanisms and effects. Next, I will discuss future prospects. First, there might be many people who are not familiar with us, but we, services for Man Yahoo. In other words, I am a facility engineer who supports facilities. The wide variety of services provided by our company, such as Line and Yahoo, by IT infrastructure, such as servers and networks, is provided. I am in charge of operating the facilities that support this IT infrastructure, such as electricity and air conditioning. Furthermore, facilities such as electricity and air conditioning are, for example, even in the event of a major earthquake or a typhoon, in order not to interrupt services, we operate 24 hours a day, 365 days a year, never stopping this. This is precisely the greatest value we create through facility operations. The Kitakyushu data center, which we operate, boasts an enormous scale. The site area is amounting to stadium after stadium. The facility capacity is an enormous scale of tens of megawatts. Within it, tens of thousands of servers are housed. How to stably operate these enormous facilities? How to operate it efficiently is a very important mission for us. Such enormous data centers consume a vast amount of power. In this way, power consumption, approximately 70% of a data center's power consumption, comes from the IT equipment itself. It is used by the IT equipment itself that provides the services. At that point, regarding air conditioning, is 25%. This is what it's called. It accounts for a large proportion, and this 25% is also a significant percentage. The power consumption of IT expenses is service usage. In other words, it fluctuates depending on the amount of service processing. The servers are generating heat in response. The cooling system, as it's called, addresses the heat generated by IT equipment. We are working to process this appropriately. The power consumption of this air conditioning system is something that we facility engineers, by optimizing operations and equipment usage, this is a large area where we can directly work on efficiency improvement. Here, how we have been working on improving the efficiency of air conditioning power. Let's look back at the history of these challenges. First, the Kitakyushu data center in its earliest days, the 2000s, we were using a typical air-cooled air conditioner called a crack. This is something you use in your homes. This is a standard air conditioner. You can imagine a giant version of this. Following that, with the increasing density of servers, in the 2010s, it can supply chilled water from a central heat source to efficiently cool servers. Central heat source method. What? The cube law and crack. In the 2020s, based on our experience and challenges with the operation of central heat sources, we have shifted to a system that supplies chilled water from distributed heat sources. Also, in line with the expansion of data centers, not only by introducing the latest equipment, we introduced water-cooled air conditioning into an old building from the 2000s, transforming the server room into modern specifications. We are also working on projects. In parallel with the evolution of these air conditioning systems, we have utilized the power of nature. We have continued to tackle the theme of how to address this. From these very first data centers in the 2000s, we are working on server cooling through outside air intake. In the 2010s, furthermore, this outside air intake, we have evolved it. Then, in the 2020s, this is based on the issues derived from our operational experience with outside air intake. We have adopted a pre-free cooling method. Furthermore, currently, we are working on reducing power consumption by combining AI security. This is a cooling system. I will explain the introduction of the guide, pre-free cooling, and refrigerant control later. We have, in response to the demands of IT equipment, evolving air conditioning requirements. Furthermore, in addition to that, the power of nature and by integrating AI-based automatic control. So, we are making progress in our journey toward global data centers. Through the initiatives I've discussed, we have reduced power consumption in this way. As I mentioned earlier, from the 2010s onwards into the 2020s, distributed heat source system. Introducing it temporarily increased power consumption, but by taking on challenges such as implementing pre-free cooling and AI control, we are continuously working to reduce power consumption. Up to this point, I have presented an overall picture of the current situation. Now, I will explain the specific technologies that have supported this challenge. First, this is a direct fresh air intake system that draws cool outside air directly into the server room. Normally, with equipment such as chillers that consume a large amount of electricity, we make chilled water, this light blue arrow. Servers are cooled by sending chilled water. On the other hand, this system also directly incorporates cool outside air, thereby air conditioning system. We are reducing the power burden and power consumption. By the way, this method also has its challenges. Moist air entered through the gaps in the outside air intake vents. The derived power increases. And also, first of all, the outside air is, depending on conditions, such as high humidity or high dust concentration. Considering these operational challenges, we introduced the pre-free cooling method as our next endeavor. In pre-free cooling, at the preceding stage of the chiller that produces chilled water, which I just mentioned, we added cooling tower equipment within the green frame. A cooling tower is equipment that cools water by utilizing the property of water to absorb heat when it evaporates. Thus, by cooling the chilled water in stages, without bringing outside air into the server room, significantly reducing the burden on the chillers. We have been able to consistently reduce the power consumption of our air conditioning systems. Up to this point, I have been introducing the hardware technology. We will apply AI-driven automatic air conditioning control to this. From here, I will introduce our initiatives. This is a schematic diagram of the AI-powered automatic control system. There are two important points here. The first is the placement of these temperature sensors. Here, on these 9 rack surfaces, we have a high-density setup. We have placed temperature sensors. This allows the servers to you can accurately measure the temperature of the intake air. The enormous amount of real-time data obtained from this, centralized in AI. We control the fan speed of the cube. The second important point is precisely this, controlling the fan speed. Everyone. Why not the temperature, but the fan speed? Some people may wonder if it's questionable to focus on that. I will explain that. This involves a physical law called the cube law, as shown in this equation. The power consumption of the air conditioner's fan is as shown in this formula. It is proportional to the cube of the rotational speed n. In other words, this rotational speed n, if you lower it even slightly, the power consumption P dramatically decreases. As shown in this graph, theoretically, by reducing the fan speed by just 25%. By reducing it, the power consumption will be cut by more than half, by as much as 58%. The role of AI is to maximize the utilization of this physical law. So how does AI determine the optimal rotation speed? The key is, with the high-density temperature sensors I just mentioned, it's about finding areas that are being overcooled. Conventional air conditioning control is 1. From the air conditioner, whether to control the blowout temperature to be constant, or based on a table that was decided in advance. The fan speed to control. That approach was common. However, with this method, the actual complex temperature management within the server room, because we are not able to properly anticipate the flow of equipment, even if a hotspot temporarily occurs. To prevent this from happening, excessively low temperatures occurred in areas like this blue section. This overcooled area, this means that electricity is being wasted unnecessarily. So in other words, to prevent this, from sensors evenly distributed in small clusters, the entire server room is controlled to maintain an appropriate temperature. The specific algorithm is as follows. AI, which air conditioner, to the temperature of which server rack, how much an impact it has. We continuously learn about the impact of this. First, what happens to the temperature distribution when the fan speed is reduced? We form a hypothesis. We made a hypothesis, and then, based on that, we predict the temperature distribution. We actually adjust the fan speed of the air conditioners. And based on the results of that adjustment, the difference between the prediction and the actual measurement is, and analyze it, relearn the impact. The optimal rotational speed is recalculated. This cycle, by continuing to do this, air conditioners whose demand is excessive, we will reduce the rotation speed of that fan. Through this initiative, we have reduced the power consumption of air conditioning fans by an average of 30%. We achieved the result of saving. The reduction in fan speed itself, as written here. It may seem like a small 5% on average. However, due to the cube law I mentioned earlier, the effect of power reduction will be very significant. Naturally, this is done without creating hotspots in the server room. It remains in an extremely stable state. Additionally, as stated below, some fans saw a reduction in rotation speed by as much as 12%. This means that over half, 56% of the power consumption was reduced in this section. When we introduced AI, we did so knowing the reduction effects it would bring. This time, in an actual operating environment, we were able to verify it. Regarding the optimization of cooling towers, we are talking about equipment. It's not about stopping it, how to rotate it optimally. How? In its original name, we stop the air conditioners with low loads. We tend to run the remaining equipment at high speeds, harnessing the cube law. Operating a larger number of air conditioners uniformly at low rotation speeds results in significantly lower overall power consumption. AI eliminates such human biases and optimize the power consumption of the entire system's air conditioning. We are able to determine the optimal rotational speed to optimize it. The verification results indicate that there is room for further expansion of AI implementation in the future. Finally, here is a look at future prospects. We are currently in the stage of partial optimization, specifically fan speed control. Going forward, we will pursue expanding the scope of AI for overall optimization across the entire data center. In the future, weather forecast data for outside air and server power consumption, we integrated those predictions into the AI system. The ventilation fans, chillers, and cooling towers. Each piece of equipment is a single unit. We aim to operate the data center as an integrated system. Up to this point, we have owned data centers of two companies, and we ourselves, because we operate it, we can explore relentless challenges. I hope this is conveyed in the presentation today. Thank you for your kind attention.